Okay, so we continue with the previous recording for a bridging problem, a piece of mass inside a rotating cone. So now we're going to look at the other free body diagram associated with this problem. So the problem is asking us to find a maximum period as well as the minimum period for which the cone could rotate, so that the piece of mass would stay intact or adhered to the cone. Okay, so now we continue to look at the free body diagrams associated with this the mass resting inside a cone, with the cone rotating about a vertical axis. So we have seen this diagram in a previous discussion, and so we're not going to go into details about this free body diagram for the case where the friction force and the normal force are opposite to each other. So now we're going to look at the other case where the friction now changes direction. So what is this about? Well, so for the mass here, all the forces acting on the mass, we have the weight, the friction, the contact force friction between the mass and the surface of the cone, and of course we have the normal force from the surface of the cone acting on the piece of mass. Now in this case, the friction force and the normal force, they are seems to be in the same. They have components which are in the same direction. So here's horizontal is labeled x, and the vertical is labeled y. So we have the x component of the friction force and the x component of the normal force. Now they tend to help each other out. They're made in the same direction. So that means the centripetal force will be greater, and as a result, the centripetal acceleration would also be greater. And because the velocity of the mass is inversely proportional to the period, so therefore a large velocity would imply a small period. And so in this particular case, the friction force is pointing down toward the bottom of the cone. So this would make it opposing the mass, so that it would not slide out of the cone. So what this means is that if the mass is if the cone is rotating too rapidly, then the mass could slip out of the cone if there was no friction involved. So here the friction force is in the downward direction, so as to try to keep the mass stay still inside the cone without slipping out to the opening of the cone. So these two forces, the normal force and the friction force, they're going to contribute to the centripetal acceleration. So here's the equation for that. Apply Newton's second law to the mass m, and so we have the x component of the normal force plus the friction component of the friction force is going to give the centripetal acceleration. In contrast to the other case, the case where the friction force is pointing toward the opening of the cone, so this would prevent the mass from falling down to the bottom of the cone. And so we have the friction force and the normal force. They tend to be in different directions, and so the respective x components would tend to subtract, leading to a smaller velocity, which would mean a larger period. So this case is for the larger period, and this case is for the smaller period. So using the free body diagram as a guide, and then we can go ahead and set up the equations, and then to be able to solve for the period, for the maximum period as well as for the minimum period.